So we are starting chapter 3 of the ISLR book, linear regression, which we already covered to some extent. We have a data set labeled x1, y1. We assume this is the data generating process. There is an intercept, there is a slope, there is some irreducible error, and we make some estimation to estimate the intercept and the slope, and we may use that to make predictions. Here's an example: sales versus advertisement, TV, and we have these data points. This is the underlying line that was estimated. These are the residuals. How do we estimate beta 0 and beta 1? Well, we solve an optimization problem, as we saw in the previous lectures, where we are minimizing the residual sum of squares. And if we plot the residual sum of squares in terms of beta 0 and beta 1, then it will look like a ball-shaped surface. I described that. It's essentially convex. And we are looking for a combination of beta 0 and beta 1 such that the residual sum of squares is the smallest. Here you see the contours. Each of these contours represent combinations of beta 0 and beta 1 for which the residual sum of squares is constant. And as we get further away from this red point, you see the contours, the values increases, so the mean residual sum of squares goes from 2.15 to 2.2 to 2.3 to 3. So whenever we are doing a regression or most of the statistical learning methods, especially those that come from the data modeling approach, they solve some sort of optimization problem, and they try to find the combination of parameters such that our cost is minimized. And cost here is the, in this case, is a residual sum of squares. Okay. So this is this figure is supposed to express the idea that we expressed in the previous lecture concerning the smoothing splines. So here the underlying relationship is linear, and red represents the true relationship, and so it's a population regression line, and this blue one is the estimate that we get from the data. Now, if we had generated another data set, we would have gotten another line. And that line would have more or less pointed in the same orientation, but it would be different. And if we do it many times, you get many different lines. So these estimated lines, there is some variability involved. And this red one is the population regression line, and the rest of the lines are the lines that you would get if you would look at a different sample from the same data generating process. So each least square lines is different because it comes from a different data set, but on average, the least square lines are quite close to the population regression line because they are all fitted to data sets that come from the same data generating process. As with, this is just reviews you've seen before. When you fit a line, you get a coefficient, you get some standard error, t-statistics, p-values, and if the standard errors are small compared to the coefficients, or if the t-statistics are large enough, or if the p-values are small enough, that means that these coefficients are statistically significant. And then the R-square, or famous R-square, the closer it is to 1, the better the fit. If this is the data generating process, the standard errors are computed for simple linear regression in this form. We already did the math for these. We can also do some hypothesis testing. The null hypothesis is that there is no relationship, and if there wasn't any relationship, then t statistics, which would have been beta hat 1 divided by the standard error of beta hat 1, would be a t distribution with n minus 2 degrees of freedom, and if the p-value is small enough, then we reject the null, so on and so forth. So these are from other courses. So I will just actually skip this part. Okay. So simple regression sales onto radio advertisement. We see that radio advertisement has a positive, statistically significant positive effect on sales. We see newspaper advertisement also have a positive, significant effect on sales. Okay, and to be specific, the units are in $1,000. So each $1,000 increase in spending on radio advertisement is associated with an average increase of sales by 2 or 3 units. While the same increase in spending in newspaper ad leads to an average increase in sales by 55 units. Okay. Okay. Now, if we move from simple linear regression, instead of trying to find a line, we're trying to find a hyperplane. A hyperplane that is close to most of the data points. So here we have 2 predictors. The red dots are our observations, and we are trying to find this hyperplane. So multiple linear regression is tasked with finding this hyperplane that is as close as possible to all the data points. So here the structure is the hyperplane. Now, if you do this multiple regression using 3 covariates, TV, radio, and newspaper, suddenly what we see is that newspaper becomes insignificant. While TV and radio are still positively associated with sales. Let's look at the correlation matrix. TV and radio are not very correlated, but TV and newspaper are also not very correlated. But TV is highly correlated with sales, radio is highly correlated with sales, and newspaper is less correlated with sales. On the other hand, radio and newspaper are correlated. I mean, 0.35 is not 0, it's not 1, but it is a reasonable amount of correlation. Okay, so let's look back here. The take-home message is that that simple and multiple regression coefficients can be quite different. As we can see, radio, the coefficient doesn't change significantly, but newspaper significantly changes, and we know that newspaper, that radio and newspaper are correlated. So what does that reveal? Reveals a tendency to spend more on newspaper advertising in markets where more is spent on radio. So markets where there's more money spent on newspaper advertising, those markets tend to also spend more on radio advertising. So now imagine that as this suggests, let's assume this is correct, and newspaper advertising has no direct impact on sales, but radio advertising does increase sales. So then in markets where we spend more on radio, our sales will tend to be higher. And since the correlation matrix shows, we also tend to spend more on newspaper advertising in those same markets. So a simple linear regression which only looks at the relationship between sales versus newspaper will observe that the higher value of newspaper tend to be associated with the higher values of sales, even though newspaper advertising does not actually affect sales. It just happens to be correlated with radio. So newspaper gets credit for the effect of radio on sales. Okay. I skipped this because this is from regression. You've seen it. Okay, so this becomes important in the next chapters. Variable selection. Scenarios where you have more observations, you have less observations than the number of predictors, or the number of predictors are so large that you know that only a few of those many possible predictors are associated with the response, but we do not know which ones. And then the question becomes, if we have p features, how many models can we consider? It's it's to the power of p, because each predictor can be inside or outside. So each predictor gives us two possibilities, and since we have p predictors, we have to multiply 2 times itself times as many predictors we have, so it becomes 2 to the power of p, where p is the number of predictors, so 2 to the power of p is exponential, so the number of models that we can consider is exponential. We cannot consider them all, we cannot look at them all, we cannot measure their performance, we cannot calculate their performance, we cannot estimate the coefficients for all of them. It will take forever. And that's why some use greedy methods, such as forward selection. So we don't have any variables, and then we add them one by one, depending on the p-value or the residual sum of square, and then we continue until a stopping rule is satisfied, like AIC, BIC are adjusted R-square, as we'll see in the later chapters. Or there's backward selection, which starts with all the variables, and one by one removes them, again, based on p-values and refitting again, and until some threshold until all variables have a p-value below some threshold. And then there's mixed versions, which go back and forth. I don't know what this is. Okay, and I will show some examples on this page, but for now this is sufficient. Okay, so let's just stop here.